Hello, it is 4 p.m. Thursday, September 18th, and I'm gonna go ahead and get started. Just as a reminder, those of you watching it off of YouTube, that the schedule has shifted. We are no longer doing our Zoom meetings on Friday. We are doing them on Thursday. I did this after sending out an announcement with a form and asking you guys to fill out the form to tell me like when your availability is, and the most common time that was available was Thursday afternoon. So decided to move it. Friday seemed to not work out for most people. At least most people are to the survey. So we are doing it on Thursday. Hopefully we can get a few more people coming into our Zoom sessions. Now, as for labs, I'm going to take a minute to remind you guys that your labs always have a discussion session section, discussion page for you guys to fill out after the lab. So the pivot is only worth 10 of the points. There's a discussion post worth the other 2 points. And participation in it is expected. Now, for most of your discussion sessions, I'm going to ask you to compare your results to one of your colleagues here in this Physics 6 class. Your results are probably going to be different than your colleagues because most of you will have, everyone receives a randomized assignment of sorts. It's all the same assignment, but the videos might be randomized. So we have different speeds, for example, on a bowling ball rolling. And I want you guys to compare your graphs to theirs and say, hey, this is what I found that was the same. Maybe you both had the same y-intercept, or maybe you guys had different slopes. Well, what does that mean exactly? So I want you guys to take the time to go through and compare your graphs to your neighbors, for example, in the last one. I do go through and I do respond to your discussion posts, and if it's great, perfect, 10 out of 10, well, I guess 2 points out of 2 points. But if it's absolutely perfect, then you'll give a response that says something like, "Hey, great job, keep it up, keep doing what you're doing." Um, if your discussion posts, if there's something that I think you could have done better, you'll see a response that says, hey, I think that you missed units, or I would ask you to, make a correction, right? And if you correct it, I'll give you full credit, right? There's nothing wrong with making mistakes, but we have to go back and make corrections to our mistakes. So, um, just be sure to double check that like the response on your post doesn't say to go back and make a correction. Uh, your grades for your first assignment should be posted and up. And your grades for your second assignment will come soon. Again, I made an announcement about this like a week or so ago. I postponed the first and second assignment because some people were a little bit late to log in or they needed a little extra time, whatever. So I gave you guys an extension. For Lab 3, we are having them due on the days that we expect them to be due. I think I made them due on Tuesdays. So keep an eye out on the due dates. I gave you an extension on the first two, so you guys have a little bit longer. Today we will be discussing the third lab, and the third lab is more focused on constant velocity motion, but really trying to dial in on this idea of graphing. Graphing is incredibly important in sciences. It tells you about the trends, it tells you about behavior of objects. We want to graph our motion and take a look at, well, what does the graph tell us? We'll look at graphs of position versus time. We'll look at graphs next week of velocity versus time, and we'll see what all of these things will lead to, what kind of information we can glean from a graph. Graphs are super helpful. Today, during this Zoom video, I'm going to be talking about the different graphs that you'll see throughout the lab and how to interpret it, and what happens when your motion changes. And today the motion is going to be changing abruptly, meaning like instant changes. Next week we'll look at smoother changes, which we call acceleration. And on that note, your next lab is up and available for you to start if you want to get a jump on the semester. This is the next few labs, so you're welcome to get a little bit of a head start. And as always, you're welcome to contact me. Let me know, hey, I need a little bit of help doing, X, Y, or Z. Even if it's a couple weeks out as far as what the due date of the lab is, you're always welcome to ask me. Um, That being said, if you jump ahead, keep in mind that the discussion posts ask you to respond to a classmate, and your classmates probably won't get there at the same time as you. So, keep that in mind that you're gonna probably have to check back on the discussion post to uh, have an interaction with your colleagues. Okay, so I'm gonna go ahead and share my screen, and we'll talk a little bit. We'll do a little bit of a lecture. Let's share the screen. Wonderful. Okay, I believe we can all see, or we should all be able to see. Slide that says measurements and motion, graphing motion. This is the idea for this week's lab. I want to make sure that we're all really confident with this idea of taking measurements and analyzing motion. When it comes to week 6 or 7, you guys are going to be more or less flying solo. So we're going to spend a lot of time on this idea of like, how do you take a measurement? How do you graph motion? And how do you gain some information about the motion graph that you created? All right, so let's see. A little bit of a refresher, right? So last week we were dealing this, and the first couple of slides are going to be a refresher. I like doing refreshers because it's helpful for us to remember what exactly it is that we were doing, because all of these labs will build on each other, right? Last week we were doing measurements of motion. This week we continue to do so. And when we look at motion, we can graph out position versus time, position on the vertical axis, time on the horizontal axis, and we can gain an idea of the motion of different objects depending on, how they're moving. So here we have a red car and a blue car, and we can see that the red car is traveling much faster. And how does this appear on your position versus time graph? Well, the fact that the red car is traveling faster gives it a larger slope on your position versus time graph. The blue car, which is traveling slower, has a more shallow slope. So that slope tells you about how quickly a car is moving in this case, or just any object that we're mapping out, tells you how quickly it is moving, right? And the steeper the slope, the faster the motion. This is going to be true almost all of the time, right? The steeper the slope, the faster the object will be going. Okay. Well, then we ask the question, this slope is so important. The slope is so important. How exactly do we measure a slope? Well, to measure a slope, we might take a look at the position versus time graph, and we might take a look at, for example, 2 data points on this position versus time graph. I'll mark out 2 in red here. And it doesn't matter which 2 you pick, whichever 2 you want to look at, you'll get the same result. And I'll prove that to you shortly. So when we take a look at this position versus time graph, we would want to know the slope by taking a measurement of its rise and its run. So I marked out in this red line, and it's a little bit of a rough red line. I'm still drawing without a tablet, so, patience, please. I appreciate it. If we look at this run, we see that this run is approximately 1 second long, right? That is just taking a look at the difference in horizontal position from 1 to 2 unit second. So we look at the position from 1 to 2 seconds. That's a change in 1 second. We look at the vertical. I mark out the vertical line. And that vertical line has a change in 10 meters. So how fast is this car going? Well, we measure out the slope by taking the rise over the run. So we take that 10 meters, we divide by the run, 1 second. And what that gives us is a slope which measures our velocity of our object. And here we see 10 over 1. Well, that's 10 meters per second. We're always careful to remember our units, right? Units are important. Units are everything. This slope. Well, I said any 2 data points will work. It doesn't matter which 2 data points you use. I'm going to prove that to you by picking 2 other data points. We'll use 0, 0 right down here. That is to say that you are at position 0 when your time is equal to 0. And we are going to take a look at the position, I don't know, let's go all the way up here to 50 meters at 5 seconds. We'll take a look at these 2. And when we do, we see that we have a run, very large run. Well, the run is from 0 to 5. That is a change in 5 seconds. And then we look at the rise, and the rise goes from 0 meters to 50 meters. That is a change in 50 meters. So you take the rise over the run and you see that the velocity is going to be 50 meters divided by 5 seconds. And when you do 50 meters divided by 5 seconds, well, that just gives you that same exact value, the same value, 10 for the numerical part. Remember, every measurement has two parts, a number and a unit. The number part is 10, and the unit here is meters per second. So it doesn't matter which 2 points we use. We could use two that are real close to each other, like a 10 and the 20-meter mark that's seen in red, or you can use 2 points that are more spread out. You can use the 0 meter to 50-meter marking. You end up with the same exact slope. So when you're calculating slope, at least on these straight lines, if it's a perfectly straight line, when you're calculating slope, it does not matter which points you choose, you end up with the same value. Now, there's something I want to take a look at next, and that's idea of what we call initial conditions. Because when we look at this car starts out at a position 0 meters at a time of 0 seconds. And that's indicated on this graph by the fact that it crosses right through the point 0, 0. We use that for our measurement of slope when we were doing the blue positions. But this initial position and initial time both being 0 is not always going to be the case. Sometimes we have the case where our initial position or our initial time are slightly offset. And when we do that, our graphs look a little bit different. They all will still end up being straight lines. So here we have 3 different scenarios where we say we have 3 different initial conditions. And in each of these initial conditions being different, we see that the graphs still resemble the same shape, namely they are a straight line. And since they're a straight line, we can start to analyze something like slope, right? We take a look at this first line and we see that there's some rise and some run. There'd be a slope, and that slope would tell us velocity. On the second graph here, we see, okay, well, it's a little bit steeper. Since it's a little bit steeper, it'd have a little bit more of it'd have a little bit larger of a slope, meaning it'd be a little bit faster. And on this third graph here, we see that, calculate rise and run, measure the slope. The slope would be a little bit smaller. So in this case, the position versus time graph would tell us that our object in this third graph is moving slow. So we have a slow moving object on the far right. We have a fast moving object in the middle. And in the left-hand side, we have sort of a medium pace, right? The slope is in between the fast and the slow. I'm not going to write medium because I'm struggling to write with my trackpad here, but you do have a fast and slow. So we can gain some information from the slope. The slope tells us a lot, tells us how fast an object is going. But the initial conditions matter as well, because when we look at this first graph on the left, we see that, well, the line goes straight through 0, 0. Since it goes through 0, 0, that means that the motion started, whatever object this is, it started at 0 meters at a time of 0. So the stopwatch started and it was at what we would call the origin. This is to say that we have an initial condition telling us that our object began at time 0, position 0. When we take a look at the middle graph, we see, well, it doesn't go through that 0, 0 point. Instead, it goes through 0 position, meaning on the horizontal line, that is 0 position, at some later time. What does this mean? This means that at 0 time, the stopwatch, whatever's timing this motion, the stopwatch begins, and it takes some time before the motion begins. This essentially means that it had a delayed start. It didn't start right when the stopwatch started, instead started a little bit after the fact. So we have a little bit of a delayed start for our object in the middle here. And when we look at the slow object, we see that it does hit that vertical line. And this vertical line that I just tried to outline in blue, the vertical line tells you about when the motion or when the stopwatch is at 0. And we can see that this line does hit that vertical line. That means that this object does start moving. It does start moving, or it is moving when the stopwatch begins, but it starts at a position much higher than 0. Well, what does this mean? This means that its initial position was further ahead than the previous ones, right? It had a head start, in other words. So we look at these and we have a head start. This far right one started further up, further ahead of the other two. So our initial conditions mean something here. One of them starts at 0 meters, the far left one starts at 0 meters when the stopwatch begins. The middle one starts moving only after the stopwatch begins and a little bit after the stopwatch begins. And the far right one, well, the far right one starts moving when the stopwatch starts moving, but the position is further ahead, meaning that it started ahead of the other two objects. So we get a lot of information from these initial conditions, and they can tell you a lot about an object and how it is moving. So then we have this idea of motion. We understand the slope means something. The vertical intercept and the horizontal intercept, they both mean something. The vertical and the horizontal intercept tell you about these initial conditions. So we get some information from these graphs of position and time. But all of these have been straight lines, and the question is what happens when the lines are no longer straight? When you have objects that are no longer following a pattern of a straight line, well, that is a case when we say we have changing motion. Changing motion is the type of motion you get whenever a graph follows a non-linear trend, meaning it's not a straight line. And that's what we have here, right? If you look on the screen, we have a graph that has straight line, sure, but then at 4 seconds, it plateaus, and then it starts climbing again after 8 seconds. So we have this behavior of a non-straight line. So our motion is changing. And what does this tell us? Well, if we look at the time between 0 and 4 seconds, we can't imagine finding a slope, right? You figure out the rise and the run. And in fact, you'd find that it's something like 15 meters per second here, I think. So you're able to find a slope here, indicating that we have a moving object. And then we look at the time between 4 seconds and 7 seconds. And between 4 seconds and 7 seconds, the object is always at 60 meters, meaning that we have an object not moving. It's always at the 60-meter position point. So since it's always at the 60-meter position point, we can say it's not moving. Its speed is essentially 0. And then after that, we have an object that is again moving, and we can figure out, what is the rise and run and figure out on the time between 7 and 11 seconds. And when we do that, we have now a speed between 7 and 11 seconds. So what does this look like? This looks like an object that is moving, then becomes stationary, and then continues to move. You might think of this as being, this wouldn't be this case because it's centimeters, it's a very small measurement, but this might be the case of imagining that you're a car approaching a stoplight, right? You are moving towards the stoplight. Let me get a different color here on my pen, so we'll look at red. So imagine a car as it approaches a stoplight. The car approaches the stoplight by moving. It then stops for the stoplight between 4 and 7 seconds, and then the stoplight turns green and you continue moving again. So you can have this behavior of changing motion. Now, next week we'll look at what happens when the motion changes a little less abruptly, right? Because this is very clear and abrupt changes at 4 seconds and at 7 seconds, meaning the change is definite. But next week we'll look at what happens when the change is maybe not so abrupt. Maybe it's a little bit more gradual. It's a case of constant acceleration. All right, so we have position versus time. Let's take a look at what this looks like with a graph of velocity versus time. So we have the same position versus time graph, and we map out velocity versus time. And there's no numbers on the vertical axis. That's because I didn't fill them in. You'll be doing a lab today that asks you to do a very similar analysis, and I don't want to fill in the numbers for you to give you the answer straight up. But when we look at velocity versus time, what do we see? Between 0 and 4 seconds, so between 0 and 4 seconds, we have an object that is moving with constant velocity. So we see that right here. Between 0 and 4 seconds, we are moving with constant velocity. Then we look between 4 and 7 seconds, and when we're between 4 and 7 seconds, we can see that our object is stationary. Again, this is like being at a stoplight. Our object is not moving. And then after the stoplight turns green, right, we now continue on with some speed, right? So we have now some positive velocity found by taking the slope of the line between 7 and 10 seconds. So we have motion here for a velocity versus time graph. Now, these velocity versus time graphs can be quite helpful because they can tell us about how an object's motion is changing, and it tells us this more directly. It says we are moving. We have some value of velocity between 0 and 4 seconds. We are moving between 0 and 4 seconds. Then velocity versus time graph can tell us we are stationary, indicated by the fact that we have 0 for these data points, right? We are stationary between 4 and 7 seconds, and then we begin to move again in that last third, and it very distinctly shows us 3 different instances of motion that we have for this object. So we have ways to handle these changing motions. And again, we'll dive a lot more into this next week. This idea of changing motion, this idea of velocity being non-constant. But for this lab, this is, as much as you need to understand about changing motion. Just understand that like velocity can't change, and it changes all the time. So we then take a second to analyze all of these graphs that we've looked at, right? And whenever we have velocity versus time graph, we've seen that it slopes kind of upwards, right? We've always seen positive slopes. We've always seen rising, right? But the question becomes, what if we have something that has a negative slope, like what we see here? Well, if we have something that is a negative slope, like what we see here, that tells us something about the motion. But first, I want to take a second to calculate the slope together, right? So we take a look at this object and we see that it starts not at the origin, but it starts at 26 meters. It ends at 2 meters. Oh my gosh, I lost my pen. Found it. So we see that we end here at 2 meters. So we start at 26, we end at 2. If we imagine a number line, well, our number line will tell us that we start at 26 and we go to 2. Well, that's moving along a number line from right to left. So we have behavior here that shows us that if we imagine a number line, we are moving leftward. Okay, well, that's going to be important. Let's take a look. Our run here between start and end, meaning how far horizontally do we move, our run is going to be equal to 8 seconds. All right, well, that's half of what we need for the slope, right? We also need to know the rise. But here's the interesting thing here. We're not actually rising, right? We are falling. If we look at this graph, we are not moving upwards, we are moving downwards. And since we are moving downwards, we say that our change is going to be negative. We have a negative rise. A negative rise just means we have a fall here. And we start at 26, we end at 2. This is a change of 24 meters. And if we calculate out the slope would be found by taking our rise, dividing it by our run, and if my math is not failing me, that should give us a negative 3 meters per second. -3 meters per second. Now, that negative is important. That negative tells you a lot. Again, we go back to this idea of a number line, and we think about a number line, and on a number line, if you imagine the 0 point right in the middle, all of the positive numbers are going to be to the right of that 0 point, and all of the negative numbers are to the left. And that is not by coincidence here that we have this negative value, because what that negative value tells you the same thing about when compared to the negative values on a number line. It means to the left. So what this negative slope means is that you are moving to the left. How quickly are you moving? You're moving 3 meters per second to the left. And when we take a look at the different types of motion we might see here, we might see position versus time having a shallow slope if we have something that is sloping downwards, but shallow. Well, what this indicates is motion that is moving to the left and slow. So we are slowly moving to the left, but if it is a steep slope like what you see here, well, that tells you you're moving to the left more quickly. Now, I know all of this motion stuff can be confusing and it takes some getting used to. Something I recommend is trying out some more practice with motion. This QR code will take you to a little game for practicing motion and comparing motion graphs to ticker tape timers, like what we saw in last week's lecture. And it can be quite helpful. Now, I'm going to take a second to go away from my share screen for a moment. And I'm going to open this week's lab. Because I think it can be helpful to take a look at the lab and walk through a little bit of it together. And I'm not going to give you any of the answers, but let's go ahead and take a look at what this lab is this week. Let's see, preview assignment. Wonderful. There we go. All right, so this week's lab on Pivot is going to have you go through a bunch of examples of graphing. So when we take a look at our lab this week, it's going to open up with a randomized graph of motion of 3 students taking a race. And this is going to be different for everyone. What you see on the screen is probably not going to be what you get. But essentially what this asks for is to analyze the 3 students and see about who finishes first, second, and third. And in my case, we can just take a look at this graph and say, well, their finishing times are going to be when they reach 40 meters, and 40 meters is right up at the top. So if it's right up at the top, what we can see here is that student 3 reaches the 40 meters first, student 2 reaches the 40 meters second, student 1 reaches the 40 meters third. So it gives you their finishing positions. So it can be quite helpful to just take a look at the actual values and think about, what do these values mean? Well, they mean that is their location at that time, and in this case, 40-meter race, when they're at the 40-meter position, and the 40-meter position is anywhere along this line, that is when they are at the finish line. We go down a little bit further. Oh, I should have cleared my annotations. Awesome. All right. And then it'll ask you, okay, well, how can we correct these so they all finish at a similar time? Sorry, that's a little bit further down. So it's going to ask you, sorry, no, where did we ask? Oh, right here. Sorry, question 7 asks you, how can you correct them so that they finish at the same time, and what will their motion diagrams look like? Well, this looks just like what we had in the PowerPoint earlier. So it's a good idea to think about, what do those initial conditions mean? Who gets the head start? Who starts further ahead? And who has to wait after this race begins running? And it just asks you to do more analyses of the graphs, right? So it says, you know, what is their finishing position, and you just take and drag them in whatever order you think that they finish in, and then you're gonna go ahead and submit the answer. And I probably got it wrong here. I just put them wherever, but you just go ahead and drag and drop these answers, and then we start to analyze the motion again. Hey, what does this look like? This looks like what we talked about in lecture. And then finally, we have a bowling ball, and this bowling ball will be the main crux of the analysis that you do today. And in this bowling ball, you will notice that it travels, well, not right to left like it did last week. Rather, it travels left to right. You're going to make some measurements, and then eventually you'll make a prediction. And after you make the prediction, you're going to see, does your prediction hold true? And if you look at the second video, it gives you the whole time of it traveling, and you'll see whether or not your prediction is true. And you're going to compare your prediction to the actual result. So that's the idea for this lab. It doesn't take as long. I think it's a little bit shorter of a lab than it was last time, at least if you're getting comfortable with this idea of measuring. It'll be a little bit quicker. But if you have any questions, please let me know. And then, of course, we have a reflection discussion post for you to take a look at. All right, I'm going to go ahead. I'm going to end my sharing. All right. Now, at this point, I am going to end the recording, and I'm going to just commence with office hours for a little bit. If you have any questions, this is a great time to ask. And then, go ahead and sign off once you're comfortable.